Hi, so here we have a problem that reads the car P travels along a straight road with a constant speed. It's given to us and the angle is also given. And we're told to determine r dot, theta dot, r double dot, and theta double dot. Well, first important note that r dot and theta dot are the change of radius here, change of radius here and change of theta here with respect to time. And then r double dot and theta double dot is the rate at which the rate of the radius changes. So this is basically thought to be our velocity, and this is thought to be our acceleration. Of course, in the respective r and theta polar coordinate angles. So first, what we're going to do is convert the value we're given of velocity to something we can work with more standardized. So we know that our velocity is equal to 65 miles over 1 hour. And we know that 1 hour is equal to 60 minutes. And we know that 1 minute is equal to 60 seconds. Finally, we know that 1 mile is equal to 5,280 feet. So working all of this out, we end up getting our velocity is equal to 95.3 feet per second. And that's all we're really given because we're going to be working in degrees. And the next thing to note is to write down our relationship equations that we know. These are derivation of these are pretty long, but we know that velocity in the r direction is equal to r dot, the rate at which this radius changes. We know that velocity in the theta direction is equal to r theta dot. Then we know that acceleration in the r direction is equal to r double dot minus r theta squared. That's r dot. And we also know that acceleration in the theta direction is equal to r theta double dot plus 2r dot theta dot. Right, so using these equations here and some basic trigonometry, solving this problem actually isn't that difficult when you consider using polar coordinates. And this is often an introduction to polar coordinates problem. So first what we're going to do is we're going to redraw this example here on a graph to have more standardized. Rather than having a picture, we're going to convert this car into a point P, and we're going to figure it out from there. So let's get our axes going. Now this is going to be standard rectangular coordinate system. This is our x, this is our y. And we're given that our origin, O, is right here. So we're going to set O to the origin of our axis, O. And finally, we're also given that this vehicle, this road that this car travels on, is 100 feet above from the origin. So we're going to mark where 100 feet is. And we're going to draw this road that this car drives on, because it's a straight line, it's not turning or anything. So that's the path of the road that this car is traveling on. And now we know that from our origin, 100 feet up, and some distance to the right the car is traveling. So let's arbitrarily put P here, just for reference. And that means that if we draw on our radius here, which is changing, this is our r, this is theta, and that's about all we're given here, other than the fact that this is the velocity of the car that's driving. So using this information, we need to convert these values into the polar coordinate system. That's where r dot, theta dot, and the rest exists. So this is our radius. So continuing this onwards, it will give us our axis, and 90 degrees from here. Because if you think of it, you have your x and y, then you have r and theta. So it's important to note that the theta axis in the positive direction is here. And I'm just going to continue this down here. And the r is already there, so we don't really need that. And this is a right angle here. Well, assuming that this is our new x-axis, we know that the theta here is also equal to 60 degrees. And now we can use trigonometry to determine what the amount of velocity, this velocity is in the r and in this case, negative theta direction. So how does this work? Well, if we draw a line that comes perpendicular to the theta axis and a line that draws perpendicular to the r axis, this is the component of our velocity in the r direction, and this is the component of our velocity in the theta direction. And this is what we need to solve for, because we can see here in our formulas, that's where we can get r dot and theta dot from, and we will need those to solve for r double dot and theta double dot. So, with the law of sines, we're going to solve for r, v of r first. It doesn't really matter what order you do it in here, you can figure it out. Although you will need to go back and substitute in different values here, so you don't want to mess with that. Anyway, well, we have Vr is equal to r dot. Well, how can we solve for r dot? Well, it turns out that we're going to need another relation, so that equals to r dot. Well, what's Vr? Well, using the law of sines, we know that Vr, so we know that sine of 60 degrees, and this is referencing this area frame here, we have this sine of 60 degrees is equal to this line here over the velocity. So it's this unknown u. So we don't want sine of 60, we want cosine of 60 degrees relates to Vr is equal to Vr over the velocity that we know. So we know this, we don't know Vr, so we can easily solve for Vr, and that's Vr is equal to V cosine of 60 degrees. And substituting in the V that we just solved for here, we know that this is equal to 95.3 cosine of 60 degrees, which ends up equaling 47.65 feet per second. And this is our Vr. Well, from here, we know that just our Vr is equal to our r dot. So we know that r dot is also equal to 47.65 feet per second. We could box that. So that's our first solution. Now it gets a little more difficult, but the same idea, we find v theta. Well, v theta is equal to r theta dot. Well, how can we find v theta? It's the same idea. This is going to be 30 degrees. So we know that cosine of 30 is equal to v theta over our velocity. And just solving this the same way that we solve for Vr, we're going to get that v theta is equal to v cosine of 30 degrees, which is equal to 82.53 feet per second. And this is our v theta. So all this is just how much of this velocity is in the negative theta direction, how much of this is in the r direction. Well, positive theta is this direction, so this is actually a negative 82.53 feet per second because it's in the negative theta direction. Now it's important to keep your axes consistent here. Well, moving on, now we need r because that's the only way to solve for theta dot. Well, what's r? Well, if we draw another right triangle here, we see that this side is equal to 100 feet, as we see up here. And using sine, we can solve for r. So we know that sine, I'm going to use a different color for here. Sine of 60 degrees is equal to 100 over r. And that is the same as writing r is equal to 100 over sine of 60 degrees, or writing that r is equal to 115.5 feet. So substituting this back into our initial equation here, we have that negative 82.53 is equal to 115.5 times theta dot. Thus, theta dot is equal to negative 82.53 over 115.5, or that it's equal to 0.715 radians per second. That's important to know. Because although we are working with degrees to solve for sine and cosine, this ends up being feet. This ends up being feet per second. And since it ends up being an angle of radians per second. So we're just going to box this one. Now we have r dot and theta dot. We're halfway there. Well, how can we find the rest of the solution? We need r double dot and theta double dot. And that's where the acceleration equations come into play up here. Well, the problem reads that it's a constant speed, which means that, so constant speed, acceleration is equal to 0. So that results in our acceleration in the r direction. So AR is equal to r double dot minus r theta dot squared is equal to 0. Well, that means that we know this side of the equation, we're solving for r double dot. Well, this is the same as writing r double dot is equal to r theta dot squared. Substituting the values that we have already solved for, we know that r double dot is equal to 115.5 times theta dot is 0.715 squared. And this just simply ends up being r double dot is equal to 59 feet per second squared. So that is the solution, the third solution. And our final solution is the theta is acceleration in the theta direction. So using that equation, we have a theta is equal to r theta double dot plus 2r dot theta dot, and that is all equal to 0. Well, solving this for theta double dot as what we want, we get theta double dot is equal to negative 2r dot theta dot over r. And substituting the values that we know for this, that is negative 2 times r dot, which is 47.65, and then theta dot, which is 0.715, and dividing this whole thing by r, which is 115.5. And if we solve this out, we get theta double dot is equal to 0.589 radians per second squared. So that is how to solve for these four values, and this is more of an arbitrary problem to get you working in the polar coordinate system, and how everything is in relation to each other, and if we actually are given the polar values, we can solve for the linear velocity as well. But it's important to know that although there is a constant speed and 0 acceleration in the positive x direction, the angle at which theta, the rate at which theta and the radius change, it does exist. There is an acceleration in the polar coordinate system. And the idea is that if we redraw this at two different points, so if we redraw our graph, and this is where our vehicle is driving, well, at t equals 1, initially, our car is going to be here. That's not supposed to be a square or a rectangle. So this is our P1. Sorry, P1. This is our R1. This is our theta 1. Well, after a certain amount of time, it's going to be over here. And it's going to be a second R. And this is going to be a different theta. It's going to be theta 2. So when looking at it from the polar direction, you do have an acceleration on theta. So you do have a rate of change of r and theta, and you do have an acceleration on that rate change. So you do have an acceleration of r and of theta. So hope this helps, and see you guys next time.